This week in lab, we're going to be learning about geologic time. So, what is the geologic record? Well, the geologic record is contained within rocks, and it is basically the history of the Earth that geologists go through and study to understand what has happened in the past. So, within this rock record, most of the rock that we are interested in are going to be sedimentary rocks. So, layers of sedimentary rocks accumulate in basically sheets at the surface of the earth, and these sedimentary rocks contain clues about what has happened on the surface of the earth in the past. The cool thing about our sedimentary rock record is that it goes back a really long time. We can go back billions of years in geologic history by looking at these layers of sedimentary rocks. So the rock record is rock. So we can go in and we can look at these layers of sedimentary rock and we can start to read them and start to interpret them based on the elements that they contain within a single layer, but also by comparing multiple layers to one another. So we have already talked about sedimentary rock. So this is what makes up most of our rock record, but it's not the only thing in the geologic record. We also have igneous rock, which we use mainly for radiometric dating, so absolute dating, which we'll be doing a little bit of in lab today. And there are also going to be metamorphic rocks, which more so help us understand processes, for instance, plate tectonics in ancient history. So, how do geologists actually read these rock layers? What do they look for? Well, in short, it's complicated. Oftentimes, our rock record is imperfect. So, sometimes the rocks have been folded, sometimes they've been broken, and sometimes layers of rock are missing entirely. So, it's a little bit complicated. So geologists start off by following and learning some of the basic ideas of geology and dissecting the rock record using either relative age dating or absolute age dating, generally a combination of both. So, relative age dating talks about when events occur relative to one another. So, there are no numbers in relative dating. We're just using basically logic and common sense to put events in order based on how they must have happened. So, for example, if you're making a stack of pancakes, well, the first thing you have to do is you have to put one pancake on the plate, and then you put another, and then another, and then another, and then another. And so it makes sense in terms of relative dating that the pancake at the bottom of the plate had to be there first, and the pancake at the top of the stack got put on there last. So we're not using any time, we're not using any numbers, we're not saying anything absolute about these order of events. We're just saying based on what we see, this stack of pancakes, the bottom had to come first and the top had to come last. So, relative dating is a big part of geology, and we're going to be working with the principles of stratigraphy to kind of get started and work on an exercise with that. The other age dating method is what is known as absolute dating. So, absolute dating is the actual time that an event occurred in years, months, days, etc. So, this is numbers saying that a rock layer is 200 million years old, or saying that this volcano erupted 300,000 years ago. So, we're using actual numbers and actual time to talk about the age of these types of events. Usually, absolute dating is a combination of two techniques. One is going to be radiometric dating, where we look at radioactive decay, half lives, and calculate ages that way. And then we can also use it in conjunction with the fossil record, so knowing when certain species existed on the surface of the earth and so on. So we'll actually be doing all three of these today. We'll be doing relative dating, radiometric dating, and fossil dating. So we're going to start our discussion with relative dating. And I said whenever geologists go in and read the rock record, we are guided by a set of laws or a set of fundamental principles of geology that help us understand the rock record. So these are our fundamental laws of geology. I've got them listed out here, and we're going to go through them individually. So the most fundamental law of geology is the law of superposition. So it tells us that if we have a stacked sequence of layered rocks, that the rock at the bottom had to be deposited first. First. The rock at the top had to be deposited last. So this is just like our pancake example. Rock layer A has to exist before B can sit on top of it. B has to exist before C can sit on top of it, so on and so forth. So whenever we see a sequence of rocks, the oldest rocks are always going to be at the bottom, and the youngest rocks are going to be at the top. So here, which layer is the oldest? Layer A. Which layer is the youngest? Layer D. Law number 2 is the law of original horizontality. So for this law, we're talking about sedimentary rocks. We've already established that they are deposited in layers with the oldest at the bottom, youngest at the top. And so this tells us that when layers of sedimentary rock are initially deposited, so when we're first creating those layers, they're always going to be deposited horizontally. So they're always going to be laid down in flat lying layers, and this is simply due to the force of gravity. So sedimentary rock layers will always be flat at the time of deposition. So they're always flat whenever they're first created. So if in the modern day we go out into the field and we see some sedimentary rocks that are no longer flat, aka they are not horizontal, then that means that they have been deformed after they were deposited. So all of our rock layers start flat. If we see sedimentary rock layers that are not flat, that tells us that something has come in and displaced them and caused them to no longer be horizontal. The law of lateral continuity, also applying to sedimentary rocks here, tells us that layers of sedimentary rocks are always initially deposited out laterally in all directions. So basically, our sediment is going to spread out in all directions until it either hits a physical barrier. So if it runs up against the edge of a basin or against the edge of a mountain, it's going to stop, or until there is no more sediment to be deposited. So basically, it'll just get thinner and thinner and thinner, and eventually it'll disappear. So what this means is that these layers of sediment are continuous. So later on, after these layers of sediment are deposited, they may start to erode. We have rivers, we have streams, we have glaciers, we have all kinds of erosive forces on the surface of the earth that want to break down these layers of rock and turn them into sediment. But this law of lateral continuity tells us that all of these were originally extended out in continuous layers. So an example that we like to talk about here is, for instance, if you go to the Grand Canyon, the Colorado River has carved out parts of the Grand Canyon and exposed the rock that would otherwise be beneath the surface of the earth. So if you were to stand at the bottom of the Grand Canyon and look to one side and then look across to the other side, you can almost in your mind start to connect up the layers. They look very similar to one another. Well, that's because they are similar. These layers would have originally connected across the Grand Canyon, and it was after they were deposited that the river came in and eroded them away. All right, law of cross-cutting relationships. So this one's really important. We're going to be seeing quite a bit of it as we work through our exercises today. So this tells us that if we go out to a set of rocks and we see a fracture, if we see a fault, if we see an igneous intrusion, so basically just a little linear piece of igneous rock that cuts across another body of rock, that the rock that is cut across had to be there first. So that's a really, really kind of wordy. So boiling it down here, rocks have to exist before they can be broken, before they can be folded, or before something can come and intrude into them. An analogy that we use here is you have to bake a cake before you can cut a slice of it. So the rock has to exist before something can cut across it. So examples of cross-cutting features just mentioned igneous dikes and sills. So that's what we have in our image over here. These are just little skinny pieces of igneous rock that come and cut across other layers or come up and sit between other layers. Faults are when we break our rock and it slides along that breakage plane. Folds are where we squeeze our rock and it changes the shape into big U and A shapes. And then unconformities are basically missing pieces of our rock record, which we'll talk about over in a couple of slides. So if we look at this diagram here, our law of superposition, we can review real fast. We've got 3 layers. Well, superposition tells us the oldest is at the bottom, the youngest is at the top. So this is time 1. We just have our nice layers. We come back sometime later at time 2, and we see that these rocks have been cut across by this igneous dike. So in this diagram, Our igneous dike would have to be our youngest feature because all of these rocks in the background had to exist before the dike could cut across them. So these are all older and the dike is younger. All right, our last law of geology here is the law of inclusions. This one doesn't get used a whole lot, but whenever it does, it's definitive and it really helps us out. So, a couple of vocab words here. Inclusion is a rock fragment or crystal that has been incorporated into another body of rock. And matrix is just the word that describes that surrounding rock. So, inclusion is the fragment, matrix is what is around it. So, our law tells us that any inclusion in a rock must be older than the rock that surrounds it. So, boiling it down, a rock fragment has to exist before it can be incorporated into another rock. So if we look over here, we've got a black chunk of rock that's surrounded by a lighter gray rock. Well, if this right here is an inclusion, that tells us this inclusion has to be older than the rock around it. So this fragment had to exist before it could be incorporated into another rock that would come around and surround it. All right, at cross-cutting relationships, we mentioned this word unconformity. So we mentioned also at the very beginning that our rock record is not perfect. It can actually be missing layers of rock. And if these layers tell us about Earth's history, missing rock is basically like missing geologic time. So if we think about the layers of Earth on the surface of the Earth, kind of like the pages of Earth's history book, an unconformity would be going in and ripping out some of those pages, removing some of that rock record, removing some of that geologic time and history out of the book of Earth. So our definition here, an unconformity is a surface in the rock record that represents missing geologic time. So AKA missing rock. Now, if we break this down, the word surface here says that uh, this is going to be a contact between two layers of rock. So an unconformity doesn't have any thickness. It's not a layer in itself. It's just the contact between two other layers. So down here we have some angled rocks, we have a flat rock on top, and the contact or the surface that separates those two is an unconformity. It's one of our three types. Now, there are three types of unconformity. We're going to talk about them individually over the next slide, but at this point you might be wondering, where did the rock go? If we're missing time, where did it go? So we really have two options here. The most common one is that there was simply nothing being deposited. So this is termed as non-deposition. Sometimes we just don't have any silt or sand or sediment to make a new rock out of, so there's just no new rock being created. Something else that we commonly see is that sometimes the rock is missing because it's been actively removed. It's been eroded and ground away and erased from the rock record. So the rock existed, but then was removed. All right, so we have three types of unconformity. We're going to go through them here. Our first type is what is known as an angular unconformity. So an angular unconformity is an irregular surface in the rock record where deformed beds, so layers that have been tilted, layers that are angular, are overlain by horizontal flat-lying sedimentary beds. Now, I'll make a little note here for an angular unconformity. All of our rocks are sedimentary, so they all have layers. Our unconformity, again, is a surface. It's a contact between two sets of rocks. So here we have this black, thick, wavy line. This represents our unconformity. Whenever we're trying to name an unconformity, we compare what's below the unconformity to what's above the unconformity. And an angular unconformity, our rocks below are going to be deformed. So basically anything that's below is no longer flat lying. We don't have flat layers down here. They've been tilted and angled. And then above our unconformity, we have normal flat lying layers. So this is an angular unconformity. We're missing geologic time here. This is due to erosion of the rock record. We have removed rock that was originally here and overlain new rock on top of it. So deformed sedimentary rock layers overlain by flat-lying sedimentary rock layers. Our second type of unconformity is known as a disconformity. So a disconformity is an irregular surface in the rock record between flat-lying sedimentary rock layers. So if we look over here, our black wavy line is our unconformity. We compare what's below to what's above, and in a disconformity, we have flat-lying layers below and flat-lying layers above. So this is just an irregular contact between flat-lying sedimentary rocks. Last but not least is our nonconformity. So a nonconformity is an irregular surface in the rock record where non-sedimentary rocks, so metamorphic or igneous rocks, are overlain by sedimentary rock layers. So non-sedimentary rocks, nonconformity, we can kind of remember that this way. So we've got our thick wavy line. Beneath this thick wavy line, we have, in this case, it's an igneous rock. How do I know? Because there are no layers within this rock. It's just one solid pattern versus our sedimentary rocks are going to be shown as layers. So this is something that's non-sedimentary. It doesn't have any layers. And it's overlain by, again, those flat-lying sedimentary rock layers. All right, so that gets us through our rules of geology and talking about unconformities. Now, our first exercise is going to be basically just kind of a logic exercise where you're going to be given a geologic diagram and you're going to have to put all the events in that diagram in order from oldest to youngest. Now, geologists, whenever we think about the rock record, we always start at the bottom and work our way up. Our law of superposition tells us that the oldest stuff should be at the bottom and the youngest stuff should be on the top. And so that's how these problems are always going to be set up. So we have our oldest event, we're going to put in our bottom blank, and we're going to keep going until we get to the top. Now, what do we mean by this word event? Well, events can be the creation of a rock layer. So each one of our rock layers in these diagrams is going to have a letter. So that counts as an event. We can also have, for example, this purple line here represents a fault. So our rock has been broken and slid past itself. So this part has slid down relative to over here. It doesn't really matter what type of fault this is, but we know that it's a fault. Uh, letter E here is an unconformity. So a bold, thick, wavy line between two rock layers. So the presence of an unconformity can count as an event. Um, yeah, I think that's about it. So that's most of our events. It's mostly going to be rock layers, faults, and unconformities. So if we want to work on this one together, we're going to break it down. Well, geologists always like to start at the bottom because our law of superposition tells us that in a sequence of rocks, the oldest rock is going to be at the bottom. So looking here, we have rock layer T, R, C, and Z. We have fault D and unconformity E. Well, at the bottom of everything is rock layer T. And I'll just make a little note. This is also rock layer T over here. Now, on top of rock layer T, we have rock layer R and then rock layer C. So we had T, R, and then C. Then as we go up, well, I know Z is on the top, but then I have to figure out what came next, the unconformity or the fault. Well, our law of cross-cutting relationship says that these rocks had to exist before they can be faulted. So we've got that here. And then we can ask ourselves, does this fault cut across our unconformity? Does it go into layer Z? Or does that unconformity sit on top of it? Well, to me, I don't see this cutting across. It stops beneath that unconformity. So it's below the unconformity, so it would have to be older. Or you could think the unconformity is sitting on top of that fault, so it would be younger. Either way, event D would be next, then E, and then the closest feature to the surface of the Earth is layer Z here. So the order that these events must have happened to produce this configuration here is our rocks were deposited, they were faulted, they were eroded, creating this disconformity, and finally layer Z was deposited on top. Another example here. So again, just kind of before we get started, it's useful to look and see what features we have. We've got several rock layers. We have another unconformity labeled E. And over here we have an igneous dike. We have this igneous arm that's cutting across some rock layers. So again, we're going to start with the law of superposition that tells us our oldest rock should be at the bottom and our youngest rock should be at the top. Well, when I look at the very bottom of my diagram, I have rock layer D and I have igneous intrusion J. Well, this is a cross-cutting feature. Our law of cross-cutting relationship tells us that these rocks had to exist before J could cut across them. So we're not going to worry about him just yet. And then that leaves layer D as the oldest feature in our cross section. Now on top of D, we have H, and then B, and then L. Sitting on top of layer L is unconformity E. Sitting on top of E is S, and then V, and then again, this dike, it cuts across everything else in this diagram. It cuts across all of my rock layers all the way up to the surface of the earth at point V. And so that tells me that it has to be the youngest feature in this diagram. So I have a question here. What type of unconformity is E? All right, so that takes care of relative dating. So we're going to go through an exercise putting those sequence of events in order, and that'll be the first part of your activities. The second part is going to focus, well, I guess the second and third part are going to focus on absolute dating. So we mentioned there are two techniques in absolute dating, radiometric dating and fossil dating, and we're going to be looking at both of those over the next few slides. We're going to begin with radiometric dating. So radiometric dating relies on the idea that atoms of radioactive elements will spontaneously decay to form radiogenic or non-radioactive elements, which are going to be known as parent isotopes and daughter isotopes, respectively. So basically, if you take something radioactive, it's going to start to break down, and as it breaks down, it produces a non-radioactive isotope as a byproduct. Now, why do we care? Turns out that this process is a good geologic clock because the average rate of decay of an isotope is relatively fixed and it doesn't vary too much. So, the rate at which a radioactive isotope decays is constant, and we know what those values are. So if we know the rate or how fast these radioactive isotopes are decaying, then we can use that to kind of backtrack and calculate the age of a rock. So scientists can use the ratio of parent to daughter isotopes and the decay rate, which is known as the half-life, to determine the age of a rock. So we've got our general formula here. It tells us that the number of half-lives that have elapsed times the length of one half-life will give us the age of that rock. And in order to find these variables, we're going to be using resources from the lab manual on page 219. So those images look a little bit something like this. So if we go through these real fast, we're given a graph, and anytime you look at a graph for the first time, read the axes. That's going to tell, or the title, that's going to tell you what's going on. So here we have percentage of parent isotopes remaining. So this is percent of the radioactive material left. And then the x-axis tells us the number of half-lives that have elapsed. So the relationship here is between percent of parent remaining to half-lives. So we're going to be using this to figure out how many half-lives have elapsed. Part B gives us some isotopes used for radiometric dating, so it's giving us some data. The way that this works is that each row of data is one piece of information, so we can read them across as a row. And they give us four parent-daughter relationships. So again, the parent is radioactive. It breaks down into the daughter at a predictable rate, which is known as the half-life. So in the example here on the next slide, as well as in the lab manual on the exercises that they give you, you will be given information about parent and or daughter isotopes. You will look here to find which one you're working with, and this is where you're going to look up basically just looking up the half-life for that parent-daughter relationship. Part C, we're not going to be using, I'm not going to be using at least. You're welcome to look at it. It's going to do the same process that we're about to go through. I think it's just a little more complicated, but that is also there in case you would like to check it out. Alrighty, so we're going to do an example problem here of how we start and go through one of these problems. So our question here tells us that you pick up a rock, you send it off to a lab, you get the results back, and they tell you that that rock has 25% of the original potassium-40 isotope remaining. Well, if we've only got 25% left, that tells us that about 75% of it has decayed into some daughter product. So I'm going to flip back to this previous slide here. So we're looking at potassium 40, argon 40. So potassium is our parent. It's decaying into argon. And here they give us the half-life length So this is a constant for this relationship here. And so that's the first thing you're going to do. You're going to figure out, are you looking at the parent? Are you looking at the daughter? And the half-life constant here. So we've got 25% of this parent remaining. Now, that might sound familiar because on our graph, the percent of parent isotope remaining was the y-axis of our chart. So we're going to be using this to see how many half-lives have elapsed. Well, if we have 25% of that parent isotope the remaining, the way that this graph is going to work is we're going to start there on our y-axis. We're going to follow it directly over until we hit the curved line. So this is our graph, our curve. And then we're going to go directly down to the y-axis, the x-axis, and read off this value. So if we have 25% parent remaining, that equates to 2 half-lives having elapsed. So if we think back to our formula, that was one of our variables, and we've got that one figured out. The next step is we need to know how long is one of these half-lives. How long is the half-life of K40? Now, we just saw that on the previous slide. We're just looking that value up. So copying and pasting that over. The half-life of K40 AR40 is 1.248 times 10 to the ninth years, which I don't know, it's hard for my brain to kind of recognize what that is. So if we write it out a little bit differently, that's 1.248 billion years. So we have our formula here, the number of half-lives that have elapsed, that's 2. The years in one half-life, 1.248 billion. So now we can solve for the age of this rock. So 2 times 1.248 billion years is about 2.5 billion years old. So that was a really cool rock. You don't want to leave that one just hanging around. 2.5 billion year old rock. So that is that. That's our second example. The second activity in the lab manual will have you calculating absolute dating um, using these radioactive isotopes and the decay formula here. All right, our last topic related to absolute dating is the use of fossils to determine the age of a rock. So oftentimes we use fossils and radiometric dating together to do absolute dating. So our guiding principle here, this is basically like just another one of those laws of geology, and it's the principle or law of faunal succession, which tells us that fossil species occur in a set order within distinct stratigraphic range, constraining the age of those rocks. Once a species goes extinct, it never reappears in the rock record. So basically, whenever a species evolves, it appears, it lives for some time, it goes extinct, and it never ever comes back again in that same form. So fossils found within the rock can help you estimate the age of the rock. Now, if we go back through geologic history, there have been millions and billions of different species that have existed on the surface of the Earth. Now, that's a lot of information, and so oftentimes whenever we do fossil dating, we're going to rely on what are known as index fossils. So these are organisms that are used as indicators or keys to specific intervals of geologic time. So again, we're going to go through an example problem here. You're going to be using this chart right here. Let me see, that is on page 217 in your lab manual. And this is what you're going to use for your fossil exercises. So hypothetical problem here. You pick up a rock and you see that it has 2 fossils in it. It has a Chonites and a Neuropterus. So we're going to look over at our chart here. Chonites is the little lima bean looking guy, and Neuropterus is this fern right here. So we pick up a rock, it contains both of these fossils in the same rock. How are we going to figure out how old this rock is? So basically it's asking for a range in years. Whenever we do fossil dating, we can't really pin down a specific year. Usually we end up with a range. So our first question is, when did Chonites exist on the surface of the Earth? So in order to do that, we're going to look at our chart over here, and for each fossil, they give you the little picture, and then they're also going to give you a vertical black line. So this vertical black line is telling us the lifespan or when this fossil existed on the surface of the Earth. So Chonites came into existence about 425 million years ago. It was around for a really, really long time, and it went extinct at about 255 million years ago. So Chonites existed from 425 to 255. Now, we need to do the same thing for Neuropterus. So Neuropterus is our fern. It has a much shorter black line here. It came into existence about 300 million years ago, and it went extinct about 280 million years ago. Now, the clutcher here is if we have a single rock that has both of these fossils within it, then that rock had to form when both of these organisms were living at the same time on the surface of the earth. So, what does that mean? We need to figure out where these two species lines overlap. So, this rock could only form when Choantes and Neuropterus both existed. And so, we're looking for the time range of overlap. Well, it turns out for this one, that range is between 300 million years and 280 million years. So that rock could only have formed during the lifespan of Neuropterus. Choantes was alive for a really long time. Neuropterus was only alive for a short time, and they only coexist where their black lines overlap 300 to 280 million years. So that is our final answer for what age range did these exist in, 300 to 280 million. All right, so the book will ask you for this answer, but then they're also going to ask you to describe this range in terms of geologic time periods. So, uh, in terms of geologic time, we can use numbers, but oftentimes you will also see words to describe certain chunks or certain periods of geologic time. So, Dr. Gibson, or I'm sorry, Dr. Dunnigan will probably go over this more with you, but if we think about geologic time, we have big chunks. We have the Cenozoic era, which is where we live, the Mesozoic, which is like dinosaurs, and the Paleozoic, which is, a lot of invertebrate fossils. We then take these eras and we break them down into smaller pieces, which are known as time periods. So for the second part of this problem, we're going to be using these little multicolored squares over through here. Now, I want to make a little note. Let me see if I can write in here somewhere. So let's take one of these squares. Maybe we'll say, let's look at the Permian, because I can actually spell that one. So if we're looking at the Permian period right here, which we're going to be looking at in a second, within this box, it's going to ask you to describe these time ranges in terms of early Permian, middle Permian, late Permian. So early time period, middle time period, late time period. Now, we mentioned before that geologists like to work from the bottom up. So early is actually going to be at the bottom of one of these boxes. So it happened early in that time period. It happened farther in the past. Late is at the top of the box, and then middle is in the middle. So I just want to put this in here because the lab manual asks you for these things and it doesn't really explain. So if we want to be able to describe the age of these rocks in terms of geologic time periods, well, we can still start with this answer here. We know that they coexisted from 300 to 280. So if we follow this over, 300 is about in the middle of the Pennsylvanian, and 280 is, I would call it early Permian. It's kind of close to the bottom there. So this time span can also be described in terms of geologic time periods, middle Pennsylvanian to early Permian in age. So when we go through these processes, they're going to give you a picture. That picture is going to have two different fossil species, and then you're going to identify them, see when they lived, find that overlap, and then describe it in terms of time in numbers and time in geologic time periods.